Yes.
So, hello everyone. Today I'll be presenting, and the topic for today's presentation is 3D printing and characterization of hydroxy-propyl methyl cellulose and methyl cellulose for biodegradable support structures. Uh, uh, this research work was done under the guidance of Dr. Quinn and Dr. Shi, and I would also like to thank Dr. Kremer and Dr. Sheng for serving on my committee. So now let's begin with the presentation. The outline for this presentation is first I'll be going through background um, about 3D printing, as this research work is related to 3D printing, and along with that I'll be discussing about the literature study in the background section, and based on literature study and background, we'll be defining our objectives. Uh, then followed by I'll be talking about the most important section of today's presentation, that is the experimental uh, design. So the first experimentation is rheological characterization of cellulose derivatives. Uh, then next experiments will be printability study, followed by the solubility test. And finally, I'll be concluding today's presentation with the important results with discussion. Uh, First, I would like to talk a little bit about 3D printing. So 3D printing is one of the advanced manufacturing technique where you can build a part uh, in a layer by layer fashion uh, from the CAD models. So the advantage of 3D printing processes is it helps manufacturers and uh, designers to cut down the manufacturing lead time and the product development cycle. So that's a huge advantage for the industry. Right now, in the market, there are various 3D printing technologies available. Uh, for example, there is FDM, there is VAT photopolymerization, there is DLS, which is digital lighting uh, system. Then there is stereolithography. So there are different kinds of 3D printing technologies available in the market. But as my research is focused on FDM-based 3D printing, so I'll summarize a little bit about FDM 3D printing process. So FDM stands for Fused Deposition Modeling. Why? Because in this build process, uh, the filament, which is of thermoplastic, is heated to its melt temperature, and then it's extruded through the nozzle in a layer by layer fashion, and it's laid on the build plate. Once the extruded filament uh, solidifies, it bonds with the preceding layer, and in that way it forms a three-dimensional part. So for any three-dimensional part, uh, in order to have complex features and intricate shapes, it needs to have a support structure. Without that, uh, the part would collapse. So as you can see in the left side uh, of the screen, uh, these are the 3D FDM printed parts with support structures. As you can see here, uh, the support structures are holding the overhang. So the role of support structure is to enable the formation of overhang beams and cavities, and hollow sections. But once the part is 3D printed, this support structure has to be separated from the build part, as it is a redundant structure, as it does not belong to the main part. So this support structure acts as a sacrificial layer, uh, and it has to be separated from the build part. So in the literature study, it was found that the currently available support materials for FDM-based 3D printing process have some drawbacks. It was in the literature study, it was found that uh, the currently available support materials in the market like PVA, high impact polystyrene or HIPS, and acrylic polymer, when used as support material in FDM based 3D printing, uh, will generate hazardous and toxic waste. Uh, because in the post processing stage, because in the post processing stage, uh, when the 3D printed part is dissolved in a chemical bath, it generates toxic waste and fumes, which is not desirable. And moreover, the uh, chemical bath contains acids and high pH value solution, which is difficult to handle and requires um, extra safety measures, like you require PPE kit, like you have to wear gloves and eyewear, so that you don't come into contact with this chemical solution. The other way of separating the support structure from the build material is using mechanical tools. Like we can use pliers to remove the support structure from the build material. But in this process, sometimes the quality of the uh, primary material gets affected. It sometimes leaves defective burrs on the primary part. And moreover, sometimes the use of mechanical tools will have leftover support material in the main part. So because of all these drawbacks uh, in the FTM-based 3D printing process, uh, there is need for finding an alternative uh, support material that can replace the currently available support materials in the market. Uh, as I discussed in the literature review, the problems with the currently available support materials are like the mechanical breakage will lead to leftover cavities in the 3D printed part, and uh, if the 3D printed part is dissolved in a chemical bath, then it will generate toxic waste and fumes due to interaction between the chemical solution and the support structure. Uh, so it's essential that we need to uh, have a much eco-friendly dissolving methods, uh, so that the toxic waste and fumes can be avoided. So based on the literature study and the background, we are now defining our objectives. So the ultimate goal of this research work is to find a biopolymer substitute for current support materials in FDM-based 3D printing. Like I said, the currently available materials have some drawbacks, and these support materials are mostly polymer, are mostly petroleum-based plastics. So, in order to have more sustainable approach, we need to replace this plastic-based support materials with biopolymers that will not only help in eliminating global wastage, but also help in reducing the carbon emissions. So, in order to do that, the aim of this research work is to characterize the effect of concentration of different biopolymers on the rheological behavior and 3D printability. So, in order to 3D print a biopolymer, we need to understand uh, what are the flow parameters, what are the essential uh, characteristics required for the part to be 3D printed. So for that reason, we'll be analyzing the effect of concentrations of different biopolymers on the rheological behavior, on the rheological properties. And finally, um, cellulose derivatives, or the material which is under study in this research work, uh, should be soluble in an eco-friendly solvent like water, because with the current methods, there is there is generation of toxic waste and fumes, and that is what and we want to avoid uh, those toxic waste and fumes. So cellulose. So cellulose is uh, is a naturally available biopolymer, and is one of the most abundant biopolymer on Earth because it is obtained from plants. Um, so the main source of cellulose uh, is the trunk of pine trees, or you can even obtain this biopolymer from refined cotton. So either pine tree or refined cotton. So for research study, we are proposing the use of natural biopolymers that will replace uh, the currently available support materials. So, uh, so we are using three different cellulose derivatives. That is hydroxypropyl methyl cellulose, which is one is E4M and one is K4M, and the third one is uh, methyl cellulose. Uh, so the commercially available cellulose derivatives, which are in the market, uh, is white in color and odorless and tasteless, and it is obtained by modifying the natural cellulose. So if you can see on the right side, uh, the picture is for uh, amorphous uh, amorphous cellulose, and below this image, there is chemical structure of natural cellulose and the modified cellulose. So if you see, uh, natural cellulose has hydroxyl groups, and whereas in order to obtain the cellulose derivatives, these hydroxyl groups are replaced with uh, either hydroxy propyl methyl group or methyl group, that is CH3. So the H is replaced either with uh, hydroxypropyl methyl group or methyl group to obtain the cellulose derivatives. And this process is achieved uh, in an when natural cellulose is treated in an alkaline solution with uh, methyl chloride and propylene oxide. So the use of methyl chloride and propylene oxide will replace the hydroxyl group to form hydroxypropyl methyl cellulose. Please let me know if you have any questions in between. Like you can stop me at any time. Uh, so, so now we know which materials we'll be using for uh, assessing the rheological characteristics uh, and 3D printing for support structures. Now we'll go for approach slide where there is a flow chart which describes the steps involved uh, steps involved in characterizing flow properties and printability. So first we'll be preparing the samples, followed by we'll be doing the rheological test to understand the flow parameters and yield stress and storage modulus. I'll be going through all this terminologies and while experiments. Uh, printed where the parameters will be optimized and uh, the best material will be selected, which can print high quality 3D printed parts. Then finally, in the experiment section, there will be solubility test where the cellulose derivatives will be tested for their dissolvability in eco-friendly solvent like water. And finally, uh, the best material will be 3D printed in order to validate the rheological uh, study. So firstly, in sample preparation, uh, samples of all three cellulose derivatives were prepared at three different concentrations. So there are three cellulose derivatives, and we are having three different concentrations for each cellulose derivative. That is 8%, 10%, and concentrations. So in all, we have like 9 samples, which will be going uh, rheology and printability tests. So for an 8% concentration, which is weight by volume, 8 grams of cellulose is used and it is mixed with 92 ml of water, which is at 70 degrees Celsius. So this mixture is then cooled down to room temperature and it is centrifuged in a centrifugal machine. So in order to make this mixture homogeneous and like I said previously, initially the cellulose is in amorphous form, but once in the sample preparation stage, we are mixing cellulose with water in order to form hydrogel. So henceforth, the cellulose will be called as hydrogels because they are in gel shape, gel structure. the rheology. So once the samples are prepared, the samples will be subjected to rheological tests in order to understand uh, the flow parameters like viscosity, yield stress, uh, which are essential for 3D printing. So what rheology does is it simulates the various forces uh, which the material will undergo during the 3D printing process. So we can, so that we can see how the material behaves when we can see how the material behaves at different concentrations. So rheometers basic schematic diagram is it consists of a stationary plate with and spindle, and there is a gap between the rotating plate and stationary plate where the hydrogel sample is loaded. So as you can see in the right side of the slide, this is the rheometer machine uh, where the rheological tests will be conducted. So the basic principle of rheometer is um, with the help of rotating plate and the spindle, uh, shearing, shearing, she, she, shear, shearing force is applied, and the corresponding viscosity and uh, yield stress and other parameters are measured. So we have used a 40 parallel plate and uh, the gap size, which is nothing but the this distance between rotational plate and stationary plate is 1000 micrometer, that is 1 close to 1 mm. So in rheology, so on the rheometer, we'll be performing two tests. The first is flow ramp test, and the second is oscillatory sweep test. So in flow ramp test, we'll be applying the shear rate uh, in a linear fashion from 1 to 30 uh, per second, and the corresponding shear stress is calculated by the rheometer. So flow ramp test gives us the data for shear stress versus shear rate, and based on this data, we can calculate the viscosity as which is nothing but the ratio of shear stress by shear rate. So tau is equal to so sorry. So viscosity is equal to tau by du by dt, which is nothing but the shear rate. And the second test, which will be done, is the oscillatory sweep test, uh, which is done to calculate the storage modulus. So storage modulus is the measure of so storage modulus is the measure of uh, elastic behavior of the material. So we want to know like how much energy the material can store, uh, which is essential in which is essential for 3D printing. In this oscillatory sweep test, uh, a sweep stress is applied with increasing range of zero point 0.1 to 200 Pascal and at a constant frequency of 0.5 Hertz. So now we'll be seeing the results for these two tests, and uh, each sample was subjected to both these tests, and uh, each test was repeated 3 times uh, for all the samples. So the first result which we get from the rheometer is the shear stress versus shear rate graph, where you can see these are the different hydrogens. Uh, these are the 9 samples which we prepare, and as you can see, 12% HPMC K4M had highest shear stress, followed by methyl cellulose, and uh, followed by, and the last one is HPMC E4M. Whereas the other concentrations, which is 8% and 10%, uh, they were exposed to lower shear stress values. And you can see on the right side of the graph, uh, this graph is used for determining if a material is a Newtonian fluid or a non-Newtonian fluid. So the shear stress versus shear rate graph, if it's a Newtonian model, that means with increase in uh, shear rate, uh, the shear stress increases linearly. So, but if you can see our graph, which is the same shear stress versus shear rate graph, it fits into the Hershey-Berkeley model, uh, which is the blue one. So we'll be using the Hershey-Berkeley model to calculate the yield stress. And yield stress is nothing uh, this area, which is on the y-axis of shear stress. So our second plot from the flow ramp test is apparent viscosity versus shear rate, which is obtained from uh, by dividing shear stress by shear rate. That is nothing but the apparent viscosity. On the x-axis, it's uh, shear rate which we have applied. So as you can see, the viscosity goes on decreasing with increase in shear rate. So this phenomena can be attributed to uh, change in macromolecular network when we are applying uh, shear rate. So the intramolecular forces get either get deformed or they are reorganized. So this property helps in extruding the biopolymer through the nozzle, because once we apply pressure in the 3D printer, uh, material should exhibit uh, lower viscosity values, and um, the, all these samples exhibit shear thinning behavior, which is nothing but with increase in shear rate, the viscosity goes on decreasing, and that helps in extruding mm, the materials or the cellulose derivatives from the 3D printer. And you can see uh, higher concentration, higher concentration, higher concentrations had higher viscosity as compared to uh, lower concentration. So, for example, 12% methyl cellulose had highest viscosity uh, as compared to the 8% methyl cellulose at any particular shear rate. So now this is the plot for oscillatory sweep test, uh, where the data was recorded for storage modulus with increase in oscillation stress. As you can see in this graph, uh, the storage modulus is constant up to a certain point and thereafter it decreases. So this phenomena is observed for all all samples. So the area where the storage modulus um, is constant uh, shows that there is no deformation in the material even after applying the oscillation stress. So once so and this region is called linear viscoelastic region. Once the oscillation stress goes beyond the linear viscoelastic range, uh, beyond the linear viscoelastic region, the material starts to deform. So that's why we see uh, uh, we have yield stress. We have yield stress that is required to cause the initial deformation for all the samples, and that's why we are adopting the Hershey-Berkeley model. Uh, and that's why we do the oscillatory sweep test to calculate the yield stress so that we can calculate the other flow parameters in the Hershey-Berkeley equation. Uh, so here I've indicated the linear viscoelastic region, which is for 8% HPMC E4M, and it's somewhere around 40 Pascal. So that's the minimum amount of stress required in order in order to create in order to deform the material, which is nothing but the yield stress. So the final rheology results are as shown in this table. Uh, so once we have the yield stress values from oscillatory sweep test, and we have the shear stress and shear rate values from the flow ram test, we can fit the equation into the we can fit the curve into the Hershey-Berkeley model so that we can get the K and N values. So here K is the flow consistency parameter and N is the flow behavior index. So once the yield stress values and the corresponding shear stress and shear rate values were uh, put into this equation, we were able to find the K and N values. So K is the flow consistency, which is which stands for uh, it stands for the degree of viscosity. Uh, so higher the K value means higher is the viscosity. So if you see the K values for HPMC K4M, with increase in concentration, the K value went on increasing. And the corresponding N value, which is the flow behavior index, went on decreasing. So N value denotes whether the material is a uh, Newtonian fluid or a non-Newtonian fluid. So, for example, uh, for the Newtonian model, uh, it's N is equal to 1. And whereas for Hershey-Berkeley model and Bingham model, the N value will be somewhere in the range of, and even for the Pauli model, the N value will be somewhere in the range of 0 and 1. It was so similar phenomena was observed for all three materials. It's for K4M, E4M, and MC. Uh, the K value went on increasing with increase in concentration, and the corresponding N value went on decreasing. So here, higher the N value means the material is more Newtonian or it's more liquid-like, whereas uh, smaller N value corresponds to more solid-like behavior. So for any material to be uh, for any material to be 3D printed, the N value should be as low as possible uh, so that it will behave more solid-like rather than liquid-like. Because if the N value is lower, then the material won't deform after the printing after the printing process is completed.
Sorry to interrupt, Prashant. You may want to move a little bit faster. You are the time. You have to do a time control outside.
Yeah. Uh, so after the rheological results, where we understood like how the change in concentration affects the flow parameters like the viscosity, yield stress, the flow consistency, and the behavior index. So now we'll be moving to the printability study where we'll see how the rheological results will play an important role in order to print high quality parts. So here is the 3D printer setup which we used for the printability study. So initially it was a FDM based printer, but we modified it to uh, act as a material extrusion based printer. As I said earlier, the samples which were created uh, were in the were hydrogels. So we need some kind of syringe that could hold uh, the hydrogen. So we are using material extrusion based printer for doing the printability study. So uh, we have uh, we have nine concentrations, that is 8%, 10%, and 12%, uh, which is for each cellulose derivatives. So uh, in this experiment, we optimized the concentration um, by doing uh, doing some dimensional analysis. So what we did here was we printed 3 lines for each sample with a spacing of 20 mm. And the morphology of these printed filaments were observed using a digital camera. And it was found that with increase in concentration, I mean, the deviation in in diameter was minimized. So, for example, the 8% concentration had higher dimension. Uh, this is because of the this was of the less viscosity as compared to the 12%. Uh,
So Prashant, you still have like 10 slides, but I will give you 5 minutes to finish the rest of the 10 slides.
okay. So based on this, it was found that the 12% it was found that 12% concentration uh, showed better dimensional accuracy, and henceforth will in the next steps, in the next experiments, we'll be only doing experiments with 12% concentration. So we did a shape fidelity test where which is used for uh, which is meant for measuring the deformation once the printing process is completed. So as you can see here, um, shape fidelity is nothing but the ratio of printed area to the CAD area. So we printed cubes with 10 mm side, and we calculated the area of the top side of the cube. And we had the corresponding CAD cross section, which is nothing but 10 mm by 10 mm. So the shape fiddle factor is nothing but the ratio of printed area to CAD. So as you can see, uh, the HPMC E4M had highest shape fiddle factor. That means once the part is printed, it will start to deform. Which, but in order to have um, a high quality part, we need to have the shape fiddle factor as low as possible. So in the next experiments, HPMC E4M was eliminated, and HPMC K4M and MCA4M 12% concentration were considered for further evaluation. So along with the optimization of concentration and rheological parameters, it is also essential to optimize the printing parameters. So the nozzle diameter was optimized uh, based on resolution. So we had 6 different nozzles, and it was found that the nozzle with the smallest diameter gave better resolution that will result in high quality printed parts. And finally, um, our goal was to use eco-friendly solvent, which will allow uh, which will allow uh, easy remove which will allow using water as a so in the solubility test, um, 2 cubes were printed with 12% concentrations, that is HPMC K4M and MC-A4M. And the cubes were immersed in a water bath, and uh, visual inspection was done for every 2 hours, and the images were captured. As you can see, uh, over every 2 hours, the size went on decreasing. It shows that the hydrogens are can be dissolved in water, and uh, this property will enable the support material to be easily separated from the build material. And finally, in order to validate the rheological and printability results, uh, we printed different geometries and shapes. As you can see, uh, we used 12% concentration, which was the optimal concentration. Uh, and we were finally able to print different shapes and um, different structures. And finally, I would like to conclude by highlighting the important findings.
I'm sorry, I have to interrupt. Time is up, so we'll stop here. And then for the committee members and all the students here, if you have any questions, ask Prashant to answer the questions.
Colleagues, I do have a question for Prashant. Are you able to hear me?
Yeah, yes, Professor.
Okay. I'm Hiko. So here's my question, Prashant. How do you think the work you have done here as part of this project will translate into your work in the future?
Uh, so like in terms of like future opportunities,
Yes.
yeah. So I'm looking for full-time opportunities in the field of like uh, manufacturing and 3D printing. So I feel like this research work has helped me in understanding the basics of 3D printing and the FDM based 3D printing technology, as well as the material extrusion based. So I think if if there is any company which is working on biopolymers or um, especially cellulose, I think this idea can be translated, and it can be moved from a like niche market to, and it can be brought into mainstream. So uh, I, I think if there is any 3D printing company which is working on biopolymers, I think this research work is really relevant, because as we know that like for example US um, for example US generates around 28.5 of plastics, which goes into the landfills every year, according to the Environmental Protection Agency. So I feel if we take such sustainable approach uh, towards manufacturing, like using biopolymers will help our reliance on petroleum-based plastics, and that will, yeah.
Thank you.
Any other questions from the audience here today?
Okay,
Can you
so
show your?
Prashant.
Yeah, go ahead.
Okay, so Prashant, can you hear me?
Yep.
So I have a question regarding those real measurements you just did. So you just talked about you did 4 rounds. to test the apparent viscosity, and also you did the oscillatory stress sweep. So what's the other that you can use within this area to really test the viscoelastic properties? Because I didn't see too much information about viscoelastic.
So like, why did I use oscillatory sweep test?
I mean, what else? What's the other method you usually is involved when you predict the viscoelastic properties of the material? That's something typically done by others, but I didn't see from your research.
Okay.
About that?
Like, you mean the storage modulus versus the loss modulus graph?
Yeah, right direction.
Like the tan delta, like calculating the value of tan delta. So I felt for this topic, it wasn't relevant because we just needed the values of yield stress, and which can be obtained from storage modulus versus oscillation stress graph. Because storage modulus versus loss modulus will only tell us the flow point, and I don't think that is required for this project.
Okay.
So I have a question. Yeah. So I have two questions actually. The first question is, so why do we care about the strings and rheology for the support material? So I would thinking, I'm not 3D printing expert. I was thinking, so you use spot material to temporarily support the structure on top when you do the 3D printing, and the structure on top, I don't think is huge. It's very heavy. Maybe you want to print very tall structure, but I don't think it's very heavy structure on top. You need to care about the strings and rheology of the support material. That's the first question. The second question is, so when you do a support material, I think the shape is more important to me. When you print this, when you build this spot material, spot, and that accuracy of the shape of the support, that may be more important because that will affect the 3D structure built on top.
Yep.
Yeah, those are my two questions. Yeah.
So for the first question, so the rheology tests were conducted to see how the concentration of how concentration affects the viscosity. So if you want to build a part which has higher height, we need to have a material which can stand on its own. Like it needs to support the preceding layers. So for that reason, I think we need to calculate the shape. We need to calculate the storage modulus. So storage modulus tells us if a material can material will deform or not after the printing process. So for example, if you can see my screen in the oscillation sweep test, methyl cellulose with 12% concentration had high storage modulus. So, and if you see the fidelity results, methyl cellulose had a lower shape fidelity factor. That means the storage modulus, if it's higher, then we can build parts with which can have higher heights. Otherwise, the part will deform. So for that reason, we need to know the rheological properties so that we can much better understand like which concentration and which material should be used for 3D printing the support structure. So now, if we use methyl cellulose, the part won't collapse. But whereas if you use HPMC E4M, which has higher shape fidelity factor and also lowest storage modulus, the part will definitely collapse. So for that reason, we need to do the rheological tests to understand much about the flow parameters and how we can link the flow parameters to printing. And sorry, what was your second question regarding the dimensional accuracy? So while printing this polymer, we made sure that we are using the most optimal concentration and the most optimal printing parameters. Like, for example, the nozzle diameter. So we use nozzle diameters, but we used the one which gave us better resolution. That is the nozzle diameter with the smallest diameter. So optimizing printing parameters and by identifying the right material, we can actually print high quality parts. And yes, obviously the dimensional accuracy will be a concern, but even for the currently available plastics, the dimensional accuracy is a concern. So what we can do is we can provide additional tolerances in the design model, and so that we can get the desired printed part.
Okay. Thank you. Yeah.
Can you also tell us your achievements and outcomes real quick?
So there are two major accomplishments which I would like to share. One was we were able to publish a journal paper in the polymer journal, which was in last year. And the one more big thing is like the Iowa State University Patent Office approved our approved patent for our research work. And so in April, this research work will be filed for US patent. So I really think it's like a big achievement for me and for my entire team.
Is there any other questions from the committee member or from the student? No further questions. Students to leave the room temporarily, and please wait for my phone call, and after my phone call, you can rejoin the room.
Okay. Should I leave?
Prashant, you can leave the room now.
I think he has done pretty good, given the concerns that you had in terms of speech and all. I think he has tried very nicely.